So what does mathematics actually describe? And the point is that there are a lot of concepts and ideas in mathematics which a priori have nothing to do with the physical universe, with nature. In other words, they don't fit into the four-dimensional space-time, you see. So for instance, in this geometric line correspondence, we talk about sheaves, not even functions, which are kind of like, okay, function is something that is rooted deeply in the physical reality. For instance, think about temperature. At every point in the room, there is a certain number, which is the temperature at that room, or barometric pressure. And so that to every point you assign a number, and that's what mathematicians call a function. So functions are very much, bread and butter of physics. But sheaves, like when was last time you saw a sheaf on the street,
Yeah.
So that's just one example. Or infinite dimensional Hilbert spaces, or periodic numbers, like these numerical systems, these esoteric numerical systems that are bread and butter of mathematics, and yet we don't observe them in the physical reality. So then, if so, what could unification mean for mathematics, you see? And so my favorite example is that I say, if Leo Tolstoy did not write Anna Karenina, nobody else would have written exactly the same novel. But if Pythagoras did not live or did not discover his theorem, we would still have Pythagoras' theorem. It would still be a squared plus b squared equals c squared and not equals c cubed. And it stays the same for the last 2,500 years. And by the way, it was actually, as it turns out, was discovered by others in other places, like in Babylon, in Mesopotamia, in China, even before Pythagoras. So, and it hasn't changed. Whereas, for instance, our theory of gravity got updated 100 years ago, from going from Newtonian theory of gravity to the Einstein theory of gravity. So there's something very special about mathematics. Some mathematicians believe that there is this Platonic world of mathematical ideas named after the Greek philosopher Plato, who I must say was really following in the footsteps of Pythagoras. These ideas really go back to Pythagoras, in my opinion. And so the question then is usually posed as, do we discover mathematics or do we invent it? And I used to be squarely on the side of like, it is discovered. In other words, there is this ideal world of mathematical objects and concepts, and we just go there somehow, almost like ESP, like extrasensory perception. Like mathematicians go there and to this ideal world and discover and bring back the fruits of those from that world. Mind you, a no smaller figure than Charles Darwin actually wrote that mathematicians are endowed with an extra sense. He actually wrote that. Closer to the end of his life, he wrote that he regretted not to have studied mathematics more as a young adult or as a child, because he wrote, and that I think is a direct quote, mathematicians are endowed with an extra sense. So there is this perception, and I have to say, as a working mathematician, you do feel it. So a friend of mine recently asked me, like, how do you experience it? How do you experience the mathematical discovery? And so the best I could come up with is that, like, imagine like there is this deep fog. So there's something there, but you don't know what. And then occasionally, some part of it, the mist kind of starts dissolving, and you see the contours of the trees or a castle or some exotic animals. And then maybe it will close again. But that's the sense that you have. You don't feel that you invent something. You don't feel that you come up with something just on your own. You feel like it's always been there, but obscured by our inability to see it. It was invisible, kind of. So there is this sense. But now I kind of also feel that mathematics is a human activity. So, and therefore I kind of like, I'm reluctant these days to just say, yeah, it's discovered, it's just out there. Because who discovers these mathematical ideas? Human mathematicians, right? And so, as far as we know, maybe some other animals too. And apparently some animals can count up to a certain number, some can't, and so on. But for now, all the mathematics that we know came from human beings. So there's something to be said about that. And so I'm kind of like, now I feel it's a mystery. It's one of those questions where it's neither and both. Like an electron is both a particle and a wave, neither and both, kind of like that. But it's a very interesting thing to think about and contemplate. So Kurt Gödel, actually, the great logician, the greatest logician of all time, as far as I'm concerned, wrote that mathematical ideas form an objective reality of their own, which we cannot create or change, but only perceive and describe. Of course, this is very close to the conversation about artificial intelligence and so on, but I'm not going to go there because we want to get to the language program. So, well, I have this one example of the universality of mathematics. I don't know if we should go there or should move more faster to the. Do
you want to say it quickly?
Yeah, so there is this idea about numbers. So just to give you a sense of how weird mathematics is, weird in a good way, I want to pose this question. Is there only one mathematics, or there are like different, imagine there's another universe, not another universe, like another exoplanet, like there is another civilization, and they have their own mathematics. What if we meet and we start comparing our notes? Is it possible that their mathematics is totally different? And so the traditional argument that it may be so goes like this. Imagine that this new civilization has like many different aliens, and then you can imagine all kinds of pictures of these aliens. So then they are like us because we see other people kind of like similar to us. So naturally, we start counting things. So numbers arise from the idea that there are many things which are kind of similar to each other. Right? But what if you have like a Solaris type intelligence? Solaris was a novel by Stanisław Lem, a great Polish science fiction writer, and it's been made into a film by Andrzej Tarkowski, and then also was a Hollywood remake of this movie, which I highly recommend the Tarkowski version, where the intelligence was this is one thing, was this whole planet was intelligent. So then the argument goes, okay, for that intelligence, there is no reason to come up with numbers, because it's only one of it. They only observe one of it. There is no need for it to develop the idea of numbers because it cannot count. There are no essential things to count. So,
understood.
Right? And so, but I have an answer to that, and I want to explain how Solaris-like intelligence would actually discover numbers, not by counting, the way we usually do, or the way we teach our kids. Which, by the way, I think it's a very there's some subtle points there that we are not properly teaching addition and multiplication, but that's another story. Let me not go there at the moment, but I can talk about it later. So here is an alternative way to discover numbers. Here's an alternative way to discover, which is more clean in some sense, and kind of devoid of the deficiencies of the traditional way of teaching kids numbers through counting. Namely, we can discover them through winding. Right. You see, so this comes from what's called topology. So I have a floss here to demonstrate. So the point is that I put it on my finger, and then I can go around. I can go once, I can go twice, I can go 3 times, 4 times, and so on. So if it's an infinitely long floss, in principle, I can wind this string any number of times. But so this way I represent all natural numbers, 1, 2, 3, 4, and so on. But also observe that I can represent negative numbers if I go in the opposite direction. You see?
Yes.
Instead of going this way, I can go this way. And so this way I can actually introduce all integers without counting, just by realizing that the topological structure, that if I cannot unwind things, because to unwind, I would have to move the string through my finger. So if I'm not allowed to move my string through my finger, then there is a distinction between winding the string once or twice or 3 times or a negative number.
In the Solaris case, what would be the analogy? The solar prominences?
So the analogy in Solaris case is that instead of wrapping a circle onto itself, or you can think of my finger. First of all, you don't need the whole finger. You can just look at the section of the finger. Right? So kind of the intersection of my finger with a plane, and then you can look at this picture that I put out on the slide, where basically the circle is just wrapping onto itself like many times, right? And so, but likewise, a sphere can wrap onto itself many times. This is much harder to imagine, because you see, you can easily see it in from the four-dimensional perspective, but in 3D, it's very hard to imagine a sphere wrapping into itself. But you kind of can grasp it by analogy, that just like a circle wrapping on itself gives us an invariant, what mathematics call an invariant, topological invariant, which is the winding number. Likewise, there is an invariant of a map between a sphere, from a sphere to a sphere. And the coverings of sphere by sphere is also labeled by all integers. Because also there are two orientations possible, so you get both positive numbers, negative numbers. This is a rough rendering of what this might look like. This is an example of what's called a homotopy group. So in fact here, this corresponds to the pi 1, the fundamental group, the first homotopy group. And here we're talking about pi 2. Every time you have a sphere, you're talking about pi 2, the second homotopy group. When you have a circle, you talk about pi 1, and that's the first homotopy group, also known as a fundamental group. Anyway, this is just a kind of something to realize how many interesting aspects of mathematics there are, which go far beyond what we use ordinarily, like counting. So what it shows is that the same concept can actually arise from different continents of mathematics. In first approach, you get to numbers through counting, so kind of from the point of view of number theory, right? But in the second approach,
seems to be evidence for the discovery of mathematics,
right? Discovery, but this is a baby version of unification. That's what I mean by unification in mathematics. That numbers, or natural numbers, or whole numbers, actually live on the intersection of two fields, number theory and topology, you see. You can discover the same numbers from these two different points of view. And to me, that's an example of unification. In other words, you're not trying to say that topology is subsumed by number theory or the other way around, but you observe that there are certain phenomena which are reflected in both fields or which are manifested in both fields. And that's why it's prized in mathematics to have this type of situation, because it gives you a different perspective. It's like you're looking at the same object, but from a different angle. And this is where a lot of great discoveries are made, when you're able to realize the same thing from these two different angles, or more, 2, 3 or more different angles. So for me, mathematics is like a giant jigsaw puzzle, where you're kind of trying to build this picture from these small pieces, without really knowing what this final picture is going to look like. And so when you solve a jigsaw puzzle with your friends, usually the strategy is to try to build like small islands. So you find a few pieces that fit together and you try to enlarge them, and your friend or if your friends do the same. And so then at some point you kind of build several islands in this picture, right? Which kind of like looks consistent. But the greatest advance happens when you know how to fit different islands together, when you play jigsaw puzzle. And it is like that. That's where Langland's program comes in. So Langland's program is like this, is a set of ideas which suggest how different continents could fit together.
As you know, on Theories of Everything, we delve into some of the most reality-spiraling concepts, from theoretical physics and consciousness to AI and emerging technologies. To stay informed in an ever-evolving landscape, I see The Economist as a wellspring of insightful analysis and in-depth reporting on the various topics we explore here and beyond. The Economist's commitment to rigorous journalism means you get a clear picture of the world's most significant developments, whether it's in scientific innovation or the shifting tectonic plates of global politics. The Economist provides comprehensive coverage that goes beyond the headlines. What sets The Economist apart is their ability to make complex issues accessible and engaging, much like we strive to do in this podcast. If you're passionate about expanding your knowledge and gaining a deeper understanding of the forces that shape our world, then I highly recommend subscribing to The Economist. It's an investment into intellectual growth, one that you won't regret. As a listener of TOE, you get a special 20% off discount. Now you can enjoy The Economist and all it has to offer for less. Head over to their website, www.economist.com/TOE, T-O-E, to get started. Thanks for tuning in, and now back to our explorations of the mysteries of the universe.